Welcome back. This is Mr. Greenstein's Geometry, and we're talking about Chapter 10, Circles, Section 6, Segment Relationships inside of circles. So let's just take this shard of Greek discus that was found when they were digging in the ground, and all they have left is this piece here, but they've taken a measure of it, and they figured out, okay, so this is the outside here, and then from here to here they've measured, and they found that this is 5 inches halfway across, and then at the halfway point they go up and it's 3 inches. But they want to find out what was the original size of this, what was the diameter, PR. So we're going to take a look at that. We're going to use inscribed angles and similarity to figure this out. So here's our problem. Here's my 5 inches across here. You know that when you have a diameter and a chord that is perpendicular to, then it splits that chord perfectly, and it splits the arc perfectly too. So this is congruent to this, and this segment is congruent to this segment. So we're going to add these two connectors here. And let's just take a look at this angle APR that intercepts this arc AR. Then let's take a look at angle ABR, and that intercepts the arc AR. Therefore, this angle here at P and this angle at B are both congruent. We can also see that we have congruent angle A here and congruent angle R here because they intercept this arc PB. So angle-angle similarity between these two triangles. We can use that to come up with ratios. So the first one is the segments of chords theorem, and this talks about how these chords split so that we get a nice ratio. It says that if you have two chords that intersect in the interior of a circle, then the product of the lengths of the segments, so the lengths of the segments like AE and EB of one chord are equal to the product of the lengths of the segments of the other chord, so like DE and EC. And that's what we have down here with this equation. EA times EB is equal to EC times ED. We can use that to then calculate this problem here. You have x plus 2 and x plus 1, so we can take that and we can multiply those two together. So x plus 2 times x plus 1 is equal to, we have on the other chord x and then x plus 4. So that's going to be x and x plus 4. There's one equation and one unknown, so you should be able to do this problem and algebraically come up with the solution. You can work on that now. The next theorem is the segments of secants theorem. And this is talking about some external angle here, so an external point, and then we're going to talk about the segments that go into the circle. The relationship for this is that the outside, EA, times the whole, EB, going all the way to the other side of the circle, is equal to EC times E going all the way to the circle D, ED. So it's the outside times the whole, the outside times the whole. Why is this? If we draw these two lines here, A to D and C to B, we can see that we have some congruence. E is there's two triangles, EBC, and then there's EAD. of those two triangles, they share one angle, E. And then if you look, B, the angle B, intercepts the arc AC, and so does the angle D. So we have angle-angle similarity. These two triangles can be used to form ratios. So there's a segments of secants and tangents theorem. If the secant segment, so this, and a tangent segment share an endpoint outside a circle, which they do here, then the product of the lengths of the secant and its external segment equals the square of the length of the tangent. So the tangent, we just take that value and square it, and that equals the outside segment here times the whole segment going all the way into D. We can use that to solve these two problems. We have the secant-secant problem with the first one. We can take 9 and multiply that times 20, because this is the full length, and then make that equal to 10 times 10 plus x. And once you have that, you can solve for x. In the second problem, we have a tangent, 16. So we're going to take 16 squared and make that equal to x, which is the outside, times x plus 8. This is going to turn into a quadratic, and you're going to have to solve the quadratic. There might be two solutions, and one of the solutions may or may not work. One is definitely going to work, and the other may or may not. So you have to decide which ones by plugging it back into the formula. We will talk about the rest of this the next time we get together.